Assalamualaikum and very good day to sir. I'm Nuri Anissa. In this video presentation for PHY150, our group will present on the effect of solar power and grid condition. I will begin with the introduction and the basic physics principle of this technology. As we look at our current situation, the world is facing a critical energy crisis due to our heavy reliance on diminishing fossil fuel. This dependency not only deplete our resource but also increase greenhouse gas emissions. This is why the transition to renewable energy is highly urgent. Among the alternatives, solar power is one of the best solutions because it is incredibly abundant. To give you a clear perspective, the amount of global sunlight that strikes the Earth in just one single hour is actually enough to cover the entire world energy needs for a whole year. Therefore, this transition is highly significant, not just to reduce our carbon footprint, but also to establish long-term sustainable energy independence. Now, let's move on to the scientific principle. The fundamental mechanism behind solar technology is the photovoltaic effect, which is the direct conversion of light into electricity at the atomic level. Sunlight is actually composed of tiny packets of energy called photons. When these photons strike the solar panel, which is made of a semiconductor material called silicon, they transfer their energy to the valence electrons. This process is governed by the quantum formula. The formula is E equal to hf, where h is Planck's constant and f is the frequency of light. When the absorbed energy is high enough, it causes electron revolution, taking the electrons free from their atomic bonds. As these electrons escape, they leave behind empty space called hole, which acts as positive charge. This movement and creation of free charge is the core foundation of generating an electric current. That's all for introduction. Now I will pass to Shaya.
Moving on to my section, I will be presenting on advanced physics and current conversions, focusing on how solar technology works at the atomic and electromagnetic levels. I will break this down into two main parts: the science of harvesting electricity from sunlight and the engineering behind conditioning that power for our everyday use. Let's start with the structure of the solar cell. Now, let's look at the foundational structure of a solar cell, known as the p-n junction. In semiconductor architecture, we have two distinct layers. The n-type layer is silicon doped with phosphorus to create an excess of free electron, while the p-type layer is silicon doped with boron to create positive charge carriers or holes. The meeting point between them is the boundary interface, where carrier diffusion begins. Next, let's look at how the internal electric field is formed. As shown in the yellow area on the diagram, when this material meet, free charge at the boundary recombine to form a depletion region. This leaves behind fixed ion that establish a permanent electric field pointing from the N side to the P side. This field is crucial because it acts as a built-in directional force to separate electrical charge later on. As we can see on this diagram, when sunlight hits the solar panel, it delivers package of energy called photons directly into the junction. These photons knock electrons free from their atoms. Due to our internal electric field, a clear separation happens. The electron flow is driven upwards into the n-type material, while the holes move in the opposite direction. This constant one-way movement through the circuit is exactly how direct current or DC electricity is generated. Now, we move into power conditioning. Here, we face a technical challenge known as the current discrepancy. While our solar panels inherently generate steady direct current, our homes and the national grid strictly operate on alternating current or AC. Because raw DC cannot power standard appliances, electrical conditioning is mandatory to bridge this gap. To convert the current, we use a solar inverter which contains high-speed electronic switching circuits to reverse the DC polarity into AC. Within this conditioning system, we apply Faraday's law in induction. By passing the alternating current through the transfer windings, we create a changing magnetic flux. As shown in the formula, This induction dynamics alters the voltage amplitude to perfectly and safely match our household grid standards.
In this slide, I'll be talking about real-world implementation of solar energy. Solar energy is used on different scales ranging from individual homes to large power generation systems. At the residential scale, homeowners install rooftop solar panels to generate electricity for their own use. Through a net metering system, any excess electricity produced can be sent back to the power grid, helping to reduce electricity bills. At the utility scale, large solar farms generate electricity for thousands of homes and businesses, supplying clean energy to the national grid. Solar power is also widely used in public facilities and small-scale applications such as solar streetlights, traffic signals, portable charging devices, and even satellites, where it provides a reliable source of electricity without relying on conventional fuels. In this next slide, I'll be talking about the benefits and the challenges. Solar energy offers many benefits because it is clean, renewable, and can significantly reduce electricity costs over time. It is also requires very little maintenance and has a long lifespan. However, there are several challenges. Solar panel depends on sunlight, so they cannot produce electricity at night and are less efficient during cloudy weather. In addition, the initial installation cost is high and the battery storage system are expensive but important for providing power when solar panels are not generating electricity. I'll pass the next slide to my teammates.
Hi everyone, I will take you through the final part of our presentation, future, innovation and wrap-up. Right now, traditional silicon panels are reaching their efficiency limit at around 22%. To break this barrier, the future of solar relies on three amazing innovations. First, perovskite tandem cell. By stacking new material called perovskite on top of normal silicon, this cell can absorb way more light, pushing efficiency past 33%. Second, transparent solar window. These are special coating on skyscraper window that absorb invisible UV light to generate electricity while staying completely see-through. And third, space-based solar power. Scientists are designing solar satellites in space. Out there, they can collect constant sunlight 24 hours with no cloud or nighttime and beam the energy back to Earth. To wrap things up, solar energy is no longer just an alternative choice. It is now a core pillar of global infrastructure. To wrap up our presentation today, let's look at three main takeaways. First, the pivot to mainstream. Is a solar power is no longer just a niche alternative or a backup plan. It is rapidly to become the main pillar of global power generation. Second, the physics synergy. The beauty of solar energy lies in how it bridges two worlds of physics. At the atomic level, we have quantum physics turning sunlight into electricity. Then we have classical physics taking over to transform and move that electricity seamless through the grid. Third, the future outlook. Now we cannot ignore that there are still challenges regarding cost and reliability. However, with the rise of advanced material